All right, hello everybody. I'm pleased to announce that LAMA's running its first author presentation. We have Ozan Caglayan here, and he studied his PhD at Le Mans University, where he focused on integrating visual modalities into neural machine translation. He experimented with several types of computer vision models and representation types, and he's continuing his work here as a postdoc with the LAMA lab that we have here at Imperial. So Ozan, please take it away. I'm very excited to see your presentation.
Thank you, Nihir, for the introduction. Okay, let me share my screen. Okay, can you see it? Okay. So yeah, as Nihir introduced, I did my PhD in Le Mans University in France on multimodal machine translation. And right now I'm a research associate at Imperial College London since July 2019. So I'm mostly interested in NLP based on neural network architectures with a slight focus on vision and language learning. Yeah, other than that, I really like to play with do-it-yourself electronics and a bit of photography. And also I want to mention that I had all sorts of hypes and flatterings about AI, ML, and NLP. That happens a lot these days. Yeah, so that's me. So now I will share the other screen. So maybe you'll see a glitch because I don't know if it'll work seamlessly. Okay, share screen. Okay, so can you see the poster?
Yes.
Yeah,
okay.
Zoomed in a little bit. So
okay, is it readable like this?
Yeah.
Yeah.
Okay, so I'll try to navigate you through the blocks in the poster. So this is a short paper presented at Calling 2020 this year, and it's called Curious Case of Language Generation Evaluation Metrics. It's a joint work with Pranav and Lucia. So in this work, we basically probed some of the widely used generation evaluation metrics such as BLEU, METEOR, CIDEr, ROUGE, and a relatively new one called BertScore. So you may be familiar with the first four of them. Like BLEU and METEOR are often used when evaluating machine translation hypotheses. CIDEr is mainly for image captioning purposes. ROUGE is also used for image captioning evaluation, but its main function is to evaluate summarization tasks. And finally, BertScore is a new metric that works in the continuous embedding space of BERT. So it's not like a rule-based script that computes statistics-based scores for each hypothesis, but it embeds the reference sentences and the output of NLG system and compares them in the embedding space using things like cosine distance. So we'll be doing a couple of experiments based on familiar image captioning, machine translation tasks and datasets. And so finally, what we observed is that first, we observed that a lot of these metrics counterintuitively favored the output of the systems when compared to human references. So we would expect that if the metric is given sentences that are actually annotated or written by humans, I would expect to see like a BLEU score of 80 or 90, like something very huge, because this is what we are trying to reach with our models, right? But we see that this is generally not the case. And in fact, the machine altered texts obtain higher scores. Also, we observed that the metrics can be quite insensitive to models that actually correctly generate some rare phenomena, or let's say in multimodal machine translation, you detect that you need a feminine article by using the image, let's say. If you don't give the image, maybe it always exploits the bias in the dataset and it just gives the masculine article. But we observed that these metrics cannot easily capture these tiny changes in the output. And finally, this is the most interesting part, we found out that if we were to use just a single sentence for all of the test set samples, irrespective of the source, like you just take one sentence from the training set of an image captioning data set, like a man is doing blah, blah, and you just copy and paste it 1,000 times because you have 1,000 images in your test set, you get very reasonable scores by all these metrics. This is very surprising. So let's look at the first set of experiments. So here we use a technique called leave one out averaging. So all these metrics, I should point out that all these metrics are able to use multiple references. Okay, so if you have a test set with 1,000 images, for each of them, we have many possible captions annotated by humans. So when we have this possibility, we can do something like the following. We take one of the reference document, like one set of reference sentences, and we just hypothesize that this was actually the output of a machine learning system, okay? And we evaluate these against the remaining references. So if we have 5 references, let's say for MS COCO, image captioning, we take one of them and evaluate it with 4 references. And we do this iteratively, okay? And we obtain an estimate number here in this equation. For BLEU, we will get an average across 5 different evaluations. So of course, this will give us some standard deviations and averages, which we can also use to compare different numbers through the confidence intervals. Let's directly look at the table. So I will try to explain the table a bit. So here we are comparing 4 different data sets. The first one is a test set from Chinese to English, like pure text-only machine translation. The second one is an image captioning system in English, the neural baby talk. So it's a quite strong model that was published around 2018, I guess. And the last 2 tasks are 2 baseline sequence-to-sequence models for video captioning. So one is captioning into English, and the last one is captioning into Chinese. And the first one, the test set, we basically took the source sentences in Chinese and we used Google Translate to translate them to English. So the system here is like the state of the art today, right? It's a machine translation system, but like one of the most powerful that is built. For the other ones, like I said, I have 2 baselines for video captioning and 1 decent state-of-the-art-ish system for the image captioning. And so the empty dataset has 4 references, image captioning has 5, and the video captioning ones have 10 reference captions for each video or sample. So RVR is reference versus reference, leave one out evaluation, and SVR is system versus reference, leave one out evaluation. So what does this mean? This means that if we look at this equation, so this was for reference versus reference, right? So there's no system output here. We just take one of the human annotators and compare it against the remaining C-1 annotations here inside the sum term. But we can do the same by replacing the system here with an actual system like Google Translate, okay? But keep the references the same and the iteration procedure the same, okay? So nothing changed in terms of number of evaluations or number of references. We just now use an actual system instead of the reference system. So this gives a way to compare how does these metrics behave if I compare human versus human versus system versus human. The numbers in pink are highlighted because they are substantially, let's say, different than the other ones. So this gives us an idea about how do these metrics behave in such a protocol. So what we notice is that in overall, in this table, the systems are actually favored much more than a reference annotator, okay? So if we take the image captioning example, if we take the person who annotated the test set of COCO and compare it against the other persons who did this, we get a BLEU of 19.5. But if we replace the system with our neural captioner, the score jumps to 30. So there's almost 11-point difference when we evaluate a system. So you can see that the trend is almost global across tasks and languages with tiny differences that are, so for BLEU and ROUGE metrics, they almost always favor the system outputs, okay? So it's all the SVRs who are highlighted in pink. So we can say that these systems are quite sensitive to frequent constructions like n-grams that happen to be appearing a lot, and they are not so, they don't really avoid lexical diversity that can happen because like we have annotations from 5 different persons, for example. But if you look at CIDEr, which is a metric that wants to ensure that there is a consensus across different references. For example, here we can see that the reference annotators actually get a better CIDEr than the Google Translate. And that's the same for the video captioning in English. But to sum up, this is important because there were some papers, mostly in image captioning, that use this kind of leave one out averaging by just focusing on BLEU 1, which is a very odd and simplistic measure that should not be used at all because it's just a similarity metric based on unigrams, okay? They were claiming that, oh, look, our system got a BLEU 1 of 70, but if we do this leave one out averaging based on the reference, we get 55, so our systems are beating human performance. But this is not really the case, okay? It's something to do with the metrics rather than the output being very good. So this was the first experiment. So in the second one, it is a bit similar to what I just explained, okay? So here we directly focus on one of the tasks, which is the MS COCO image captioning, okay? And we still assume that one of the human annotators, we took it as a hypothetical system, okay? Like a super AI, let's say. But we take these captions in the first set of reference captions, like let's say that the document is denoted with R1 here, and this is just a set of captions provided by an annotator for the MS COCO test set. So we take this document and we create 5 different versions, and in each of these versions we just replace the most frequent token with a token that is not seen across the sentences, let's say unknown, unc, or whatever, just some dummy token, okay? Basically, we mask the information and replace it with something that doesn't exist or that doesn't mean anything. So these 5 versions are basically versions that mask the nouns listed here. People, sorry, not nouns, but let's say words. People, standing, sitting, man, and the article a. Obviously, like there's an order in terms of the frequency here. So the A is the unigram that occurs the most aggressively across the data set with 16.7% of all words. Okay, so let me repeat, we have this set of reference captions here from which we take each of these words and we replace it with a dummy token unknown. And for each of these variants, we evaluate against the remaining references, the verbatim references. So we don't touch R2, 3, 4, and 5. These are the test set captions that are coming from MS COCO. But we only take R1 and create 5 different versions with some of the tokens masked. So what does this mean? We'll see how losing the ability of presenting some frequent unigrams exhibit changes in the metrics produced, the scores produced by these metrics. Okay, so if you took a look to the paper, this plot doesn't exist in the paper. So this was particularly created for the poster, and it was a bit late to include it in the paper. So that's why I wanted to also use the poster to present. So I think this is a much more readable way of presenting this result. So what does this mean? Like on y-axis, we have our 5 metrics, and the x-axis denote the relative drop in each metric with respect to R1. So what does this mean? So if you take the actual R1 and you don't mask any of the tokens, you get some BLEU score, okay? And then if you remove all peoples in R1 with unknown and you reevaluate, there's a drop in the metric, and this is the relative percentage of that difference in the metric. So what happens here? So if we look at the variant where we mask all of the articles A, so this is the most aggressive type of pruning here, we see that BLEU almost loses like 55% of its score. Okay, so more than half of it just drops. But if we go upwards, we see that CIDEr is a bit less sensitive to such frequent unigram substitutions. ROUGE is a bit less sensitive than CIDEr, and it goes on like this. We see that the continuous space metric BertScore is the least sensitive to such masking phenomena. But here we see that for all of the other tokens, like people, standing, sitting, and man, the differences are not that, the drops are not that substantial. So it's not linear at all, okay? But for people, of course, since this is a relatively less frequent token, although it's the fifth most frequent token in the data set. So you see that it's quite unremarkable. Okay, so this will lead to the next set of experiments where we will use this information in a different way. So to sum up here, so if you had a system that is able to produce some very rare tokens, let's say you did a fancy beam search algorithm that you use for integrating an external vocabulary during domain specific decoding, and you're able to put some terminology specific to the task for some nouns. I mean, it's quite easy to overlook such differences that can be quite important actually when you use these metrics that takes into account the overall corpus statistics. But in a follow-up experiment that is some sort of a contrastive experiment, so we can also ask the following question. Okay, so you replace the most frequent token A with an unknown token, but what will happen if you don't just replace A, but you randomize the words that you want to replace, but you reach the same amount of frequency, which is 16.7. So this means that like you sample words randomly and you drop these words, you replace them with unknown as well, and you stop doing this when you hit the percentage of masking threshold, which is 16.7. But why is this important? Because when you mask randomly, it's likely that you will hit semantically more important words, like you can hit people, girl, dog, cat, actions, or verbs, whatever, which tells a lot more than the article A about the performance or readability of a sentence, okay? But this will give us an estimate of how these metrics are actually evaluating sentences that are just missing the article A. So if I were to read a full test set captions where the article A's are missing, I could easily understand what's the image about, right? But if the maskings were random, that's not the case. I could easily miss cat in a sentence, like Unk is running on grass, okay? But I could not tell what the image is about. If we look at the behavior of the metrics to such phenomena, let's start with BLEU, okay? We see that the drop in the BLEU metric is not that high when compared to dropping the article A. So this is something that is really disappointing, because this means that for BLEU, it doesn't matter that you drop cat, dog, people, standing, etc. randomly. You will get a much better score than consistently masking the article A everywhere. So this shows that BLEU and CIDEr and ROUGE here, so these three metrics, all of them for this new experiment, so the light gray, the random masking, the performance that they lose is sometimes slightly less than the masking of the A token, but for ROUGE and BLEU, it is substantially less. So they don't really care about semantics, okay? All they want is to be able to hit more and more unigrams or bigrams or whatever that they will count. But for METEOR and BertScore, and especially for BertScore, we see that in the continuous embedding space, it is much more important to have words that have actual meanings, let's say, rather than function words like the A. So if you do this experiment for BertScore and METEOR, we see that they tend to lose more for the random masking experiments rather than the article masking experiment. Yes. So yeah, okay, we say that the METEOR and BertScore tend to care about semantics rather than frequencies.
Ozan, do you mind if we interrupt you for questions, or would you rather we pass them at the end?
No, I think you can interrupt me.
Okay, cool. So I just have a question. Could you just clarify what BertScore actually is?
So BertScore, so basically like it's a pre-trained like BERT checkpoint, okay, BERT model.
Mm-hmm.
And you give it your hypothesis sentences, okay? And the BERT embeds them and you get the CLS token, or you get the hidden representation for every position in the sentence, right? Mm-hmm. Think of it as the final layer outputs of BERT. And we will also have some latent outputs for the reference sentences, okay? Mm-hmm. Let's consider that you only have one reference for each hypothesis. Basically, you can compute a attention matrix where you will have the words in the output of your system at the y-axis, and on the x-axis you will have the words in the reference. So what it does is that it computes the dot similarity or cosine similarity between the latent states for the hypothesis words, and also so they compare the latent state representations in terms of cosine similarity, and you get some sort of
over the whole sequence
map, right?
Okay.
For the whole sequence. And from that heat map, it just, I'm not familiar with the details, but it computes a metric that tells you that, okay, this reference sentence is closer in meaning to this sentence rather than the other one. So it gives you a number between 0 and 100 based on the semantic similarity.
Yeah, so loosely, it's just a cosine distance between the embeddings of the reference and the system.
Exactly, yeah.
Okay, cool. Just while you're on this diagram as well, like you mentioned, well, like research seems to put a lot of emphasis on quantitative analysis. And as you said, with your example of A, you know, if you look at something qualitatively, the sentence can make sense without the A. So how can we, when we're doing research, how can we or if we're reading research, how can we ensure like the validity of the metrics which are being reported when they're so sensitive to input sort of common words?
Mm-hmm. This is a nice question. I think the main thing to do is to present some examples called qualitative analysis to see what's going on the real side rather than just looking at numbers. Another thing that can be is the human evaluation, of course. Mm-hmm. Like to take a set of sentences and ask human annotators about their quality or their adequacy with respect to what's happening there.
Are you worried about researchers like hacking or optimizing for quantitative metrics when?
But that's already what we are all doing in a sense, mm-hmm. right, in the field. So sometimes we tend to read new papers like this, which are like warnings to the researchers. We say that, okay, just let's not look at numbers that much, but at other times, most of the paper actually, like we present tables with such numbers, right? I think there should be a balance between quantitative and qualitative analysis. But I think the issue here is that here we are really trying to push the metrics to some corner cases, right? We are injecting some noises that are substantial or maybe minor. And these experiments showed us that these metrics are not perfect. So this can be useful when designing metrics. It's like some sort of a set of adversarial attacks that some people who want to design a new metric can take into account.
Mm-hmm. So you're not like saying these metrics are useless. You're basically just saying that there are cases where they can fail, and we should take good caution when we use these metrics to make sure we're not.
Exactly. Yeah, that's the point. Yeah.
Okay, cool.
For the normal functioning regime where you have a system that produces decent captions or translations, the behavior is not that erratic, right? But if you have some sort of weird phenomena that maybe you are trying to make an AI model better on some very, very rare phenomena, and you rely on this metrics and you see that, oh, the metrics doesn't improve at all, but maybe you're looking at the wrong place.
Yeah, I saw a paper recently the other day, which was doing it the other way around, or doing kind of what you said, but the other way around, in that they reported the metrics, but they didn't report any qualitative examples. So they said, oh yeah, our methodology includes the BLEU score for machine translation or something like that. Yeah, you know, it didn't show any examples. So that kind of got me wary about, like, you know, how much can you trust these results, which show just the quantitative results and not the qualitative results.
Yeah, exactly. Like, we should always be looking at both quantitative and qualitative sides of the story.
Thank you.
Okay, so the third experiment is very similar to what I just described. Okay, the difference is that instead of relying on the frequency of tokens that we are replacing with unknown, we still rely on training set counts of some tokens, but we don't look at absolute frequencies of particular tokens. So this may be a bit hard to explain, but think of it as you restrict your lexicon or vocabulary by removing some words that are not that frequent based on the number of occurrences in training set. Okay, so you can say that, okay, all the tokens that occur less than 30 times, I just remove them. Okay, and here we'll compare the full vocabulary model that doesn't do such elimination of the tokens in the test set captions to some other variants where the models hypothetically are not able to generate some set of words. So this is important because of the same facts that I highlighted. So let's say that you want to generate a caption where you really want to highlight an object in the image, but that object looks similar to a hat, let's say. But in some language, you don't say hat for that particular object, but you say something more specified. But this token, the new one that you have to generate, maybe it just happens 2 or 3 times in your training set. So the models is not really able to discriminate between a particular type of hat, and during test time, maybe it's not able to generate this token. So here, if we look at the numbers, maybe it will become a bit more clear. So if you consider a particular set of tokens that did not occur more than 30 times and you just remove them, okay, these are like rare tokens that can be important with respect to lexical diversity, actually. And you compute all these 5 metrics, you get the first set of results that you hear, okay, that you see here, like 19.8 BLEU, 24.25 BLEU. But then hypothetically, let's say that your model became much more powerful in terms of producing some more diverse tokens or surface forms, okay? Because here we did not discard all tokens that occur less than 30 times, but only less than 10 times. So our knowledge about the word, our lexicon actually now has more words inside. But look at the improvements that you get. So the percentage of words that you must is almost halved, okay? So you have way less unknown tokens in your output, but the improvement that you get with respect to BLEU is less than 0.1. Same for METEOR, for BertScore is 0.005. And much more strikingly, if you just don't remove anything at all, okay, you just take the reference captions for COCO produced by the human annotator and you just don't change anything at all. So this corresponds to the R1 here, okay? So 2 variants of R1 where some set of tokens are removed compared to the verbatim R1 that you don't remove anything. Again, we see that like we added 1.5% of tokens back. So let's say that the model is now able to discriminate between 5 different types of hats or different breeds of cats and dogs, etc. But you get a BLEU improvement of 0.16. Again, the same for METEOR. And so nothing substantial. So everything is unremarkably, the improvements are unremarkably low. So if you were to maybe apply some sort of statistical significance testing based on BLEU scores or METEOR scores, it's likely that the tools out there would say that, okay, these differences are not significant, but you actually now are able to put out some words that you weren't able to generate at all. So this brings us to the final experiment, which is a bit different than the other ones, because here we don't play with the reference sentences. We don't do any kind of masking or leave one out averaging. What we do here is quite simple, is that we find one sentence in the training set that maximizes the BLEU score in a test set. So you can say, okay, how is this possible? But it turns out that it's actually possible. So to clarify the procedure, let's say that you have a training set of 1 million sentences, okay? And you just, for image captioning, this is what you have in terms of linguistic modality, right? You have images and you have captions that are paired with each image in the training set. So the search is exhaustive here. So you iterate over all of the 1 million captions in your training set. You take each of them, you duplicate it as the number of test set images you have. You construct a new, let's say, text file that has the same sentence replicated multiple times. You give this to BLEU and you give your reference sentences for the test set, and you get a BLEU score. So you do this 1 million times. So it was quite slow actually. And then you take the sentence that produced the highest BLEU score. And we call this like a single representative sentence or single sentence. So this is something like the majority class baselines in classical machine learning tasks, a bit similar. So if we look at the actual results here, so again, here we present results for an image captioning dataset in English, Flickr. We have the video captioning MSVD. We have the VTech video captioning in English and Chinese, image captioning in Japanese for Coco, and a dialogue dataset, daily dialogue, where sequence of conversational sentences that happens to be some dialogues. So here we can also see that we did not restrict things into only English. So in terms of the language, we tried to cover different languages as well. Again, here in this table, the numbers in pink are what interests us. The other ones are not that substantial maybe. But if we just take a look at this case first, we see that if you caption all of the videos in the MSVD test set by just this sentence, okay, a man is playing, that's all, okay, you get a BLEU score of 31 almost, and a METEOR of 23.4. But if you just fetch some early state-of-the-art models from the literature, like this one, the flow model, this is an actual video captioner, okay, that takes in videos, extracts features, and produces a different caption, hopefully a different caption for each video. The METEOR score is, so they only provided METEOR numbers in the paper. So the difference is less than 1 between this dummy output and an actual captioner. But if you look at the recent state-of-the-art on this data set, of course, the result is 35. So it's quite high. But I mean, it is still not that high. If this system gets 23.4 under this metric, METEOR, something that is actual something that is actually captioning the videos, we would expect to have, I don't know, 60 or 70 when compared to 23. It's less than double actually here. The same things for the BLEU number. So I can't see, okay, let me put it here. So in ROUGE, I mean, this gets almost 60% on this data set, state of the art is 71. So what's the problem here? The problem, one of the problems here is that the reference video captions are not very diverse. They are very short, okay? And if you just happen to fulfill the n-gram counts, basically you get something out of it. And I mean, there's not much diversity in terms of bigrams, trigrams, etc. So that's why the situation is not that serious compared to, so the situation is much more serious here compared to some other datasets where hopefully the captions are a bit more diverse. Let's look at the dialogue dataset, which is quite interesting as well. So if you just put out the where do you want to go, just as a sentence that's coming from a dialogue system. Okay, so you always ask where do you want to go, that's all. And if you take the numbers, you get a METEOR score of 11. But if you just check this paper, which is actually a sequence-to-sequence baseline for this dataset, an agent that were able to do an actual conversation rather than producing always where do you want to go, where do you want to go, got a METEOR point of 9.7 and state of the art is 11. So does this mean that these systems, if you just open what has been produced by these systems rather than looking at numbers, they are actually producing very bad conversations? But if you just don't look at them and produce some numbers like this, and you say that, oh, our system gets 11.1, but the baseline sequence-to-sequence system, the score is 9.7. So we improved the state of the art by almost 2 points. This may look reasonable, but if you just add this line here, maybe this tells us that, okay, all of these systems are basically garbage or gibberish. Okay. Like finally, if you look at a relatively recent data set, again, with video captioning, but this time every video here, each video here has 10 captions. So this is quite diverse. This should have been quite diverse, right? We often don't see that many number of references in the NLP datasets at all. But here as well, we see that if you just take the sentence in a room and then in black is dancing, you get a METEOR of 22.5. But if you take the baseline sequence-to-sequence model in the actual paper of the WATEC, so in the paper where they introduced the dataset, they also trained some sequence-to-sequence video captioner with attention, using action features extracted from the video, you get 25. It's only 2.5 points better than compared to our dummy single sentence system. And if you look at the BertScore here, that is assumed to be a much better metric because it works using a pre-trained BERT model. It knows better in terms of semantics rather than simply counting n-grams, etc. We see that it is also affected by such adversarial sentences, right? You get 53 here, but the baseline gets just 60, just 7 point better. So I would expect that the BERT score here, at least since it doesn't rely directly on n-gram statistics, I would say that, okay, this is nowhere near the reference caption that I have here for this video, but apparently maybe because of the function words that are matching in the cosine similarity space, or maybe representing words in context is not actually that good because words in context may have similar latent representations between two sentences, let's say, but in the end, for a given video, they can be totally out of sync, right? And so here, the interesting thing is that, okay, not only the n-gram statistics-based metrics are affected, but a relatively recent metric based on large-scale pre-trained BERT model also gives us some decent numbers when they encounter the same sentence over and over again. So, okay, in conclusion, so in this short paper, we showed a couple of experiments on image captioning and machine translation test sets, basically, in different languages such as English, Japanese, and Chinese. And first of all, we saw that the metrics are often behaving in a way that they favor the outputs of machine learning systems rather than favoring the reference annotations. Second, we saw that if the tokens, so we saw that the metrics tend to be quite sensitive to highly frequent n-grams, such as the article a or the word man. But in contrast, if you were to interpret this from the other perspective, if your model is now able to produce some rare linguistic constructions, like let's say it's able to fix gender marking in the target language. In that case, they are not that sensitive, and the differences are quite unremarkable. And finally, we saw that some sentences that you can get from the training set that are fulfilling the co-occurrence statistics, let's say, such as like a man is playing, with that single sentence, the metrics are easily able to produce some signal, let's say, some metrics that are in the same range for some metrics with baselines or even some decent AI models. So finally, we say that handle the automatic evaluation metrics with care and don't over-rely on them, especially on cases where you're trying to show something very rare, let's say, in terms of linguistics phenomena. And just maybe you may want to look at each sentence about what's going on, or try to come up with some fine-grained probing ideas where you just check the availability of a particular token rather than computing the BLEU score or METEOR score over all the corpus. Yes, okay. So that was all from my side. Thanks for listening. And if there are any questions, just unmute yourself and feel free to ask.
Thank you for that talk, Ozan. For me, it was definitely a little bit eye-opening. I have a couple of questions, but if anybody else does, please feel free to shout them out.
Yeah, hi, I've got a quick one. Thanks for the talk, Ozan. Yeah, I also thought that was super interesting, and it was quite relevant to me because I spent some time last summer working on text summarization evaluation metrics. I guess from a high level, I was wondering, do you see there being a case in the future where these automatic metrics can kind of fully replace the job of human evaluators, or do you think that you'll always need human evaluation side by side? Like there's not really any situation where they'll be quite good enough to fully automate that role?
I mean, I think the most healthy way of doing the evaluation is, of course, human evaluation. I think the main problem there is that how will we be sure that a given automatic metric is always producing a sensible score that could be equivalent to a human annotator? So it's like, I mean, you're in an open field, right? I don't see a way of not giving out side-by-side human evaluation or automatic metrics, because I would always be curious about, okay, what humans are actually saying in this case. I think the question is, how can we come up with a proof that the metric is actually reached a human level understanding, maybe through some sort of Turing tests, etc. But it has been shown that, I mean, approaches that actually passed Chinese room experiment or Turing test, whatever, may not always reflect human level understanding at all. From my perspective, I think that we should always look at what people say. And if the other way around happens, I would be quite attentive to what's going on and not directly accept that as a given. Let's be skeptical, right?
Yeah, I think that's fair enough. Yeah, I mean, I was just getting your opinion on it. Thanks for that.
Welcome.
Just to extend that a little bit, like surely things like BERT scores and what I'm seeing in some works of adversarial measures, so for example, be like taking a system generated caption and a reference caption, feeding both of them to some model, and the model will try to identify whether the system generated caption is valid based on the references that it's been trained on. These kind of seem like, you know, we are using neural models to quantitatively evaluate other neural systems, and how those neural models have been evaluated are by, in some cases, going to be these metrics which aren't ideal. So yeah, like should we be reporting evaluation metrics which are neural based?
Which are neural based?
Yeah, like BertScore.
Like BertScore. I mean, ideally, this is why people come up with these, right? But in practice, this doesn't happen quite fast way. We tend to use these metrics that are quite easy to get some numbers, and these are Perl or Python scripts or Java toolkits, etc. You don't have to install a massive amount of dependencies, or you don't. And for BertScore, if you run it on CPU, it takes quite some time to get some number. So if that's really useful, or if we'll benefit from it, it's almost always a good thing to add one more metric to your inventory, right? But the fact that they are working in continuous space, we should take that with a pinch of salt, because I just came up with a case for the previous question, like, can metrics be human level so that we just don't rely or require automatic human evaluation at all? Let's consider what happens if in one of your sentences you have the color blue for something, and also as a adversary or in the reference you have black. And BERT obviously works in BP level, right? So it will, at some point, for novel things, it will split things into 2 or 3. And if, let's say, hypothetically, in the vocabulary, you don't have blue and black, and it gets split into a token that is BL and ACK for black, and for blue, it's BL and UE. So in the cosine similarity space, just for this BL token, you will get some score, right? But does this mean that the prefix being the same, semantically, the words should be the same? I mean, not really, unless you are really hitting the root of the word, let's say the verb, but this is not guaranteed in BP or sentence piece. I mean, you have all these sorts of tiny noise introducing things going on, and add to that named entities, right? Completely novel thing that BERT never saw, like the president of a country, let's say, that just has been elected last day, and this wasn't someone known to Wikipedia, someone new. What happens when BertScore evaluates that completely new token? I mean, we don't know in context. So yes, it may be good to have these numbers besides rule-based metrics, but I mean, I don't think that. So if you look at the actual papers that introduce metrics, you will often see that the validity of the metric is defined by correlation numbers with respect to human evaluation. On the normal regime, where you don't try these fancy or erratic experiments, okay, all metrics that are introduced obtain some sort of correlation with respect to human evaluations broadly. But what happens if you try this sort of stuff going on? So probably they will just break down completely. So, okay, in short, I mean, let's report all of them, but be careful. One final example, like when I was preparing the poster, I tried some more experiments with BertScore, and GitHub, they had a new version than the one that I used for the paper, the first submission. And when I computed the numbers with the new version, I mean, all the numbers completely changed. I mean, look, this will never happen with BLEU, right? So the whole idea is to always get the same numbers, but we don't know what happens with these metrics if you have a new version of transformers or a tokenizer. And that was the case with BertScore. I created an issue in their GitHub and then said that, oh, we switched to the new version of Hugging Face tokenizer. And apparently there was some change, and that's why you get this thing. I mean, we should be really careful. Like,
yeah, I see your point. Is like we should be checkpointing these models and saying, yeah, it's like BertScore 2020 or something like that, and then have that model fixed for a whole year.
Yeah.
Just one final question, and that is, these like more count-based evaluation metrics such as BLEU, have you seen any work, or would they work, or what's your intuition if we remove stop words, both from the system generated and from the reference lists? So I can imagine like a lot of the scores, you know, the system generated outputs could be a man with the word in or is or something like that. And so would a lot of the reference generated, the reference sentences as well. So if we were to remove stop words and really kind of just look at the words with a lot of semantic meaning, do you think we'd be reporting more accurate metrics by doing such a thing, or would it just be a moot thing to do?
So if we consider this experiment, for example, where we try to replace infrequent tokens, I think for such probing experiments, the results would be a bit more better and intuitive rather than the ones that we presented here. But I mean, in the normal daily usage pattern of these metrics, I assume there are some metrics that do that already, like removing some stop words, etc. Not BLEU, but I mean, why not even for BLEU? But maybe the impact will not that be nonlinear that you would expect, because you are removing some tokens from both the references and the hypothesis. Obviously, for the single sentence where you just take a man is playing and you duplicate it, maybe you will get a behavior for BLEU that is much more sensible, because you won't have a and is, so you won't inflate the number of n-gram hits.
Mm-hmm.
But yeah, why not? It's some sort of like a bag of words BLEU score that doesn't have the syntactic connectors in the sentence. It can be useful for things like maybe image captioning. Yeah. I don't know much insight, but it's an interesting idea.
Okay. Cool. Thank you.
Thank you for having me for this session.
Yeah, not a problem. Thank you very much for presenting, Ozan. So guys, if you're not following our Twitter, or if you don't know, our website is live. That's llamaai.io, and our Twitter is llamaai_io. So please give us a follow. And yeah, we'll see you next week.
Thank you.